Those are your choices. Screens are on now, so I'm going to try one more time here. But you keep working. It's going to block them. I can't see. Oh, yeah. I didn't mean to put that one down. Seriously, this thing is like... Right. Oh, for all of them. So it's all and 2 methyl. And the reason why this is number 2 is
Yeah.
Does this count as the fourth one in a butane?
Yeah, this exchanges. So that's
Yeah.
alcohol, right?
Yeah. But like, you know, it says butane, 2 mol. So the butane, like I'm trying to get 4 carbons. Does this count as the 4th carbon? Or am I, does this count as the 4th carbon?
No, that's part of this. I think
So you need one more.
Yeah.
Okay.
All right. That should be enough. What do you think? A, B, C, or D? D. Exactly right. This is here, the right answer. In some ways, you could do this based solely on number of protons in unique environments, right? So you're looking for something that has a bunch of unique environments where the aromatics have 5 hydrogens, so it would have to be a mono-substituted aromatic, right? And then you have 2 environments with 2 H's, right? An exchangeable OH, and then 6 H2-methyls that have the same chemical shift, right? So if you wrote out these molecules, right, so this is 1-ol, so that would be this, 3-methyl, 3-phenyl, so that would be something like this. So this is a possibility based on unique environments, right? Because this has an OH, 2 unique sets with CH2s in them, right? And then 2 CH3s that are identical and a mono-substituted aromatic, so that's a possibility. B here is 2-methyl, 3-phenyl, 2-butanol, so 2-methyl, 3-phenyl, so something like this. There's nothing on there that has 3 H's, right? This would have to be a 3H environment, this would have to be a 3H environment, this would have to be a 3H environment. There have to be 3 of them, I guess is more my point, nothing on there. There have to be 3H environments. There are no CH2 environments, right? So that's out in a multiple choice way. The next one is 3-methyl, 2-phenyl, 1, 2. So in this case, I would need to have my isopropyl unit in there. My 6H would have to be a doublet. I'd also have to have something in there that's 1H that doesn't exchange, right? This carbon has a hydrogen on it, a 1H that doesn't exchange, because that's the 1H exchangeable is my OH. So the last one that you know is this one, which is 2-methyl, 4-phenyl, 2-butanol. So this guy also matching. So now I have to discern between the 2 of them, right? So I'm going to look at this CH2 here because it's next to what I would say is on a carbon next to an environment that would influence it, okay? Meaning This one circled in D is going to be next to a weak electron withdrawing group. This one that I've circled in A is next to a strong electron withdrawing group. Note I'm not at this end of the molecule, because this end of the molecule doesn't have a hydrogen on the carbon directly next to that oxygen, right? So its influence is out after that. That induction falls off really fast. So when I parse between these two, I see that I do not have anything next to a strong electron withdrawing environment, right? I have nothing between 3 and 4 parts per million on my NMR. And so, because of that, this answer has to be out. Okay? So everyone understand what I mean? Yes? Okay. I believe this is just random. It's not very random that I chose this exact molecule, right? It has the same formula as something on your homework, right? And I think a lot of you were coming up with this as a potential answer, right, to that structure G. Everyone know what I mean about structure G? And that's not the right answer to structure G, right? Okay? Because structure G would have started with this alkene, and if you used a phenyl group to open that with a Grignard, right, a Grignard reagent that is phenyl in nature, followed by H plus or H3O plus, you would have wound up now with something like this, right, where this would have had to attach to the less substituted environment. Does everyone understand what I mean? This is part of what we'll be reviewing today, but this is actually the answer. Are there questions? Is there a brave soul who wants to ask a question about this? Because there are some of you that are looking out there like, whoa, yeah.
How does the phenyl work as a electron withdrawing group? Is it like very big or?
The phenyl group is a weak electron withdrawing group. There are a bunch of weak electron withdrawing groups. Okay, they include a cyano group, so C triple bond N, a carbonyl, so directly next to a carbonyl of any variety, a ketone, an aldehyde, an ester, those sorts of things, and then this phenyl group. Okay? Yes? Okay. All right. So in terms of the homework, there are some things on there that you absolutely should know. Does anyone want me to go over some of the homework answers before we start class? Yes? Okay, well I don't have the homework, so you're going to need to give it to me. Sorry. I have it somewhat memorized. We can start with what I have, and you guys can correct me as I go. These will be graded and ready for pickup on Monday, but just in case, we can go over it. I'll always put out a call if you want to go over it. I'm always happy to talk about it before we get going. But you started with starting material in the middle, and your starting material should have been something like this, right? Okay? So the first thing you had to do, really, was what is my starting material? I mean, you could have started with any of the spectra and tried to get some structures, right? But this would be a good place to start because it's the starting material, right? Okay, so in this case, we had 2 reaction arrows, one moving left and one moving right, that got me to isomeric molecules that had formula C5H10. So I would quickly say C5H10 has 1 IHD, right? 1 IHD. So this means C5H10 is some ring structure, right? So pentane, cyclopentane, or methyl cyclobutane, something like that, right? Or something with a pi bond. So, pentene or some substituted alkene of some variety. Now, it should make sense because you know very few reactions, right, with rings, alkanes, cycloalkanes. Pretty much the only thing you can do with them is brominate them with a halogenation reaction, right? So something like Br2 in light. That's not very useful, right? So that's obviously not going to lend itself to the large branched tree. So I need to really be working in these alkene units, right? So the bottom line is to start from here to get to an alkene, I can get to 2 different alkenes, right? The first alkene I can get to is this one. That would be pulling this proton, right? If I pulled this proton, it would lend itself in this direction, right, in an E2 reaction. Now I want to remind you that if I want to pull the proton from the less substituted carbon, I always need to use T-butoxide. It's a way to get the less substituted alkene. So I need to use a bulky nucleophile, something like this, in order to pull that proton and move this way toward this alkene, okay? More likely, any other base you use, right, is going to actually pull this proton. That would move you in this direction in an E2 reaction to give me this alkene. And they are isomeric of one another, and they both have the formula C5, and that's what makes them isomeric, right? They have formula C5H. Okay. Are there questions about this? This is a reminder about getting the less substituted alkene versus the more substituted alkene.
Why would it go through an E1 because it's at a tertiary site when it goes through carbon cation formation?
Okay, great. So E1 actually is always going to give you only one alkene. E1 is only ever going to give me this. If you did E1 in this direction, that's totally fine. But E1 will never give me this alkene in this direction. There's no way to get this way in an E1 reaction. Now, the other thing I can say about E1 is this. E1 is the most pitiful of all of those reactions because it's the least competitive of them all. E2 is the biggest competitor. At a tertiary site, it's very easy to run an E2 reaction by utilizing any charged nucleophile. So really, you can use OH minus this way, and that might be the way that you always think, or methoxide, but I can use CN minus, or I can use F minus. I can use any charged nucleophile to get an E2 reaction to run at a tertiary site. E2 is a really strong competitor, okay? Are there other questions about this? Okay, so then there were two offshoots from this where you had structure, right? One of them was to use, we were just talking about this, the Grignard, that is phenyl magnesium bromide. You do not need to show how to make the Grignard, you just slap it in there, right? That's what you want to do. Now, when you add to, actually I guess you need first to make an epoxide, right? So a lot of you use that MCPBA. It's not my choice. It's not the first thing that flows off my tongue or my mind. MCPBA is fine. I usually use a peroxy acid. That's the first thing that flows from my head. So I'm just telling you, MCPBA, same thing. Good enough, okay? So first you need this, and then you need to open it, right, with a Grignard, and finally you need to acidify this molecule. So step by step, right, so this has 3 unique steps. I first am going to make the epoxide. I'm just showing the regiochemistry here. So I'm just going to make the epoxide. That's step 1. Yeah?
I was just wondering why phenol MGBR, like, does it have an O when does phenol MGBR have an oxygen in it?
No, because that's phenol. Phenol is like just a ring.
Oh, okay.
Yeah. That's a great, because it doesn't make sense, right? Why is pH? I don't know why. Yeah.
Can we use peroxide reaction?
Peroxide as a peroxyacetic acid or a peroxybenzoic acid? Yes, that's fine. MCPBA is probably what I bet 90% of you use, right? How many use MCPBA? Yes, see, that's the organic chemistry second language for you, right there. Okay, so anyway, we move on. And so after the next step, I need to add the Grignard, right? The Grignard's going to add to the less substituted side. That's the last things that I'm putting on your review sheet, right? That door prize from today is to remind you there's 2 ways you can open epoxide ring. You want to open it on the less substituted side. That's called nucleophilic ring opening. This indeed is a nucleophile. This is like a benzene, right, with an electron pair on it and a negative charge. It's a nucleophile now. All nucleophiles will attack at the less substituted site, and so in the end, I get my pH anti, right, my O minus up here, and all I need to do then to get to the alcohol is to acidify it, right? To get the H on there, I just need to throw in some H3O+. Okay? Going in this direction, this might have been the easiest one we had there, and that was 2-butanone, right? The first thing you need to note is that chain is smaller than the original chain, right? 5 carbons in the original chain, 4 carbons in this product means a cleavage reaction, right? That's the only way you know to reduce the chain length. So in this case, actually, surprisingly, you could have done ozonolysis followed by zinc mercury or whatever reductive agent you learned in the past, or you could have used permanganate too. Either of these are actually going to get you to this because it's a dye-substituted side that we're following through on, okay? Now, it does have another product, right? It does have another product. It would be, I guess, formaldehyde in ozonolysis, and it would be CO2 with the permanganate reaction. We're ignoring that, right? And that's very common, to sort of ignore one of the products that we're getting. You get a lot of products, and we only want one. So we actually go in and isolate just that one. So we're ignoring anything that we would consider then to be a byproduct. Okay? That's the questions I got in my office yesterday. All right. So coming this way, I think in this direction, this was an ether up here, if I remember properly. This was this ether you solved for the NMR. This is what you get. So the question is, how do you get from here to here? The easiest way to do that is CH3OH followed with some acid, not followed by, with some acid. That's just like H2O H+. It's just an alcohol H+, that makes an ether instead of an alcohol, okay? You could have also used mercuric acetate with an alcohol, also fine. Both of those were on the door prize that you had already been in possession of. Next, it gave you that you went down and you added HBr and peroxide, which I did purposely put this on this weekly quiz because I forgot to put it on the door prize you got originally. This is the complete door prize now. Does everyone see it says complete at the bottom? And I believe I was smart and remembered to put on that peroxide. Am I right? Should be there. Please tell me that I'm not dreaming this. I wasn't in my office dreaming this. There it is. Whoop! All right, here we go. Go down from the alkene all the way to the bottom. Does everyone see that? HBr and peroxide. It's there now. Now it's really complete. It's really right. Okay? So sorry I forgot that last time, but it was purposely done so to remind you. So once you do HBr and peroxide followed by T-butoxide, you're going to get this alkene, which is indeed isomeric with the other two. And then you had to follow through. The hardest one was probably this way, right? Because this gave you, should have given you something like this. This is K. Is that right? K? All right, K. This is the spectrum for K. There was a lot of discussion about where this oxygen belongs. The one that I pointed to, where does that oxygen belong? Does it belong on the side with the long chain or on the side with the methyl, right? And the answer, it belongs on the side with the long chain because it's the CH2 group that's far downfield, that's showing that it's next to the strong electron withdrawing group. It's not a CH3 group that's downfield between 3 and 4 parts per million. So chemical shift alone should have guided you toward this molecule. This would have taken HBr and peroxides followed by acetate in an SN2 reaction. This is the way that you know to go. Some of you may have Googled this and may have found out that you can make an ester by making a carboxylic acid and then doing Fischer esterification. How many people did Fischer esterification? Anyone? Anyone? Yeah, okay, yeah. Google is your friend sometimes, right? That one probably wasn't that hard to figure out if you Googled. But this is the way that I was thinking most people would go. And then the last one was an alcohol. Is that right? Was it this guy? An aldehyde. Okay, you had to go through this to the aldehyde. This was actually what it was. That's right. Okay, that's why I couldn't remember. So it was an aldehyde out here, right? In this case, you needed to proceed through this alcohol to the aldehyde, noting that the chain is still intact. There's still 5 carbons in that chain, right? So it's not an ozonolysis reaction. So this would have been one arrow to that molecule, but the synthesis goes through here. You would have done BH3 followed by H2O2, OH minus, H2O, and then PCC. Cannot use permanganate, cannot use a chromate reagent. Well, this is a chromate reagent, it's modified chromate reagent. PCC is the only thing that you know to do that. Okay? Are there questions about this? Okay, the homework seemed intimidating at first, right? Yeah? How did it work out for you in the end, though? Do you find that you've learned some?
Yeah.
Yeah?
Good review.
Yeah? That's my method. I intimidate, but then you learn, and then we're all happy. So the intimidation came first, and now you've learned, and now you're happier than you were before the intimidation. Am I right? Because that means you've learned something, and the pre-assessment is coming, so you're going to kick some butt, right?
Yep. Hopefully.
Come on. Okay. You're all a tough crowd. I don't know what it is, but you're tough, man. Okay. All right. So barring any homework issues, I'll put the answer sheet online, okay? And I'll also grade these. You can pick them up Monday morning, or you can wait till discussion. I remind you that next week we only have one discussion day. And that's Tuesday, right? And when everyone leaves discussion on Tuesday and then they leave class on Wednesday, they're all going to give Kim a high five because she's got a big presentation next Thursday that she's nervous about. So every time we see her next week, we're going to be like, can I get you anything? Are you good? Good luck. All right? Everyone with me? To pay it forward, we can all be nice to our fellow humankind. Yes? Yes, tough nuts. All right, so today we're in here for pretty much riding into our last days of review, okay? I'm going to start with the E1, E2, SN1, SN2 stuff. I'm still folding in Chapter 17, so I'm still going to be very Chapter 17 focused. If you haven't yet read Chapter 17, that's going to be something you want to do this weekend. You want to read Chapter 17, okay? It'll help clarify some of the notes, right? And it is an expectation for that pre-assessment next week, okay? We're not breaking the bank here. Chapter 17 isn't that bad, okay? So I'm going to backtrack, because last class we were talking about SN1, SN2, E1, and E2 at these centers that are considered benzylic and allylic, okay? But I do want to talk just very briefly about how to get halogens on those benzylic and allylic centers. So if I start back with, say, toluene, I'll show you toluene here in a minute. You're not expected to know who that is. If I start back with toluene, okay, this is it. It's a benzene with a methyl off of it called toluene. You are going to need to know that when we get to the aromatics chapter. That's not yet. But I'm just going to start trying to use some naming so that you get a little bit comfortable with it. Toluene, if I start back here, and I want to create an alpha center at that benzylic site. So I want to create an alpha center for substitution at this site, right here. Okay, that being the alpha site. You would say, okay, one thing you can do is you can halogenate that baby, right? You can add a Br on there. Okay, way that you know how to do that is likely Br2 and light. Hopefully you remember that Br2 and light will always substitute at the most, will always substitute a hydrogen at the most substituted center, right? Now, that means, in essence, the reason is because it's the most stable site for a radical to form. What you need to know now is that the radical is most stable at these benzylic and allylic sites, right? Because carbocation stability and radical stability are the same thing. So, what I guess I'm trying to say is definitely, if I were to look at, say, a tertiary radical, I would know that this is not as stable as, say, a benzylic secondary radical. This benzylic radical that's secondary in nature, it being benzylic, right, once removed from the benzene, is now more stable. This is more stable than a tertiary center. So if you had a molecule that had both those components in it, so let's say I was something like this, okay, and you tried to brominate through a radical reaction, selectively bromination is going to happen here because that radical is more stable than the tertiary radical at the other end, okay? Really, that bromination always happens off the more stable radical element, or intermediate, okay? So, you would think to brominate this with Br2 and light, all right? And that would give you a substitution through a radical mechanism, right, off that carbon there. Now, these are not the best conditions to use when we have benzene or alkenes in our molecule, okay? Br2 alone, you know, actually has the capacity to serve as an electrophile, right? Think back. I look at my EAR reactions. You know that if I looked at this reaction, my alkene was the nucleophile, Br was my electrophile, and I did an addition reaction, right? So Br2 has the ability to serve as an electrophile. And so we want to avoid that at all costs. We do not want to have an electrophile present in these reaction conditions because this benzene is full of alkenes that can potentially react with that electrophile. And it would be the same thing if I had an allylic site, right? I'd have to be very careful because it can add across the double bond. I do not want that. So now, Chapter 17 identifies for you a new reagent. And the new reagent is called, we simplify it, NBS, which stands for N-bromosuccinimide, okay? N-bromosuccinimide. Really, it's just a very different, or a different molecule that does the exact same thing. It will brominate at these benzylic and allylic sites selectively. Same thing with this molecule, right? If I went back and I just had my hydrocarbon, it will always selectively brominate here. Does it through the similar radical mechanism, but what happens is there's no Br2 in the pot to serve as an electrophile to do any addition reactions that we might worry as a byproduct of our reactions, okay? So this is a chapter 17 piece, and we now know that when we're trying to brominate at allylic or benzylic sites, we're going to selectively use NBS over Br2 and light, okay? NBS is usually enough. You don't generally need to add the light and heat. That's okay if you don't have it with NBS. It's sort of implied because NBS is a very specific type of reagent. It's only used in that. But you're going to lose a couple points if you start using Br2 and light instead of NBS. So then the question that comes to mind is, could I use NBS in just a regular old alkane? And the answer is yes, you can. So maybe my point is to sort of train your brain to instead think of Br2 and light, to think of it as NBS. So one thing you might want to do with your cheat sheet here, right, the door prize from today, is to knock out something you learned in 231 and start putting in the 241 component. The molecule here that we're looking at is propane, which is sort of at maybe 11 o'clock, right? No, yeah, about 10 or 11 o'clock on your sheet. It's just propane, and there's an arrow to the left that says Br2 and light or heat. That's what H nu or delta means, light or heat. Knock that off and put in NBS. That's pretty much the only change we make from one to the other. Yeah?
Is that NBS and or like?
No, that's what I'm saying. You can actually add just NBS. And NBS is just a very specific reagent. It's only ever used to do this, right? To brominate, to substitute a Br for a hydrogen. That's all it's ever used for. Br2 is used for other things, so you have to add that lighter heat so you know what it's doing, right? So NBS will do the same thing. That's the one edit that we're going to make here now that we're folding in Chapter 17 knowledge. Okay? Are there any questions about this? This is simple fix, right? Simple fix. Yeah?
And is it just exactly the alpha site?
So what it's doing for us now, how I started this whole conversation, is it's creating an alpha site. What NBS will do will always substitute a hydrogen from the most substituted or most stable radical site and put a Br in there, right? We can show more examples, and we can certainly see on the weekly quiz how that's going to do that. So in this case, we have, with NBS, created an alpha site, right? Okay. So the second clicker question today was, if I add H2O and heat, okay, H2O and heat, what mechanism will this reaction proceed by? Your choices are, because it's an alkyl halide, your only choices really are SN1, SN2, E1 or E2, okay? So the question is, which mechanism is it going to proceed by? That was the actual clicker question, and then we're going to talk about what the product is. So if we think through this process, right, we're going to try and consider what it's going to be. So what do we think? That site I would classify, the alpha site, as
Secondary benzylic.
primary,
Benzylic. That's what I
benzylic.
meant.
Okay. It's primary because that site only has one carbon attached, right? It's benzylic because it's on the carbon directly attached to the benzene. So it's primary benzylic. So now I have to think, okay, a primary benzylic site is similar to what on our decision tree?
Secondary.
A secondary site, exactly. It's similar to a secondary site. Now there's going to be a caveat here, which hopefully you're going to catch on to really quick, okay? So, all right, so it's similar to a secondary site. Great. Now I think, okay, got to go to the nucleophile. H2O is derived from H3O+, okay? Conjugate acid H3O+, pKa below 0, right? So this is what I would consider a weak nucleophile, right? First, classify the alpha site. Second, consider where I would classify this nucleophile. So I'm going to classify this as a weak nucleophile. So now I see I have a weak nucleophile primary allylic site, which you've told me to think of like a secondary site, and I have heat in the system. What is the mechanism by which this is going to proceed? That's what you all want to say. Yeah, can't do it.
SN1.
Someone tell me why E1 can't proceed here. Yeah. You don't have a hydrogen to lose from the beta site, right? So, okay, we try and start working through this. So I get this. I'm putting in all hydrogens that exist in this structure. I know this is way beyond you, but it's going to be helpful to see. So now I have something like this. This is my carbocation, my alpha site. There are 2 hydrogens here, but there's no hydrogen at the beta site, is there? Nope. Okay, so this is a lesson learned. Okay, every example is a lesson learned. The lesson learned here is that a primary allylic or benzylic site can't ever undergo E1 or E2, right? A primary allylic or benzylic site can't ever undergo E1 or E2. So now that I know that, because I see that there's no beta hydrogen, this is my only beta site, and there's no hydrogen on it, so E1 is out, I got to backtrack. So now I come back around, and I'm thinking, okay, I only have my substitution mechanisms now, right? SN2, SN1.
SN1.
SN1, and why is that?
Yeah.
Because it's a weak nucleophile. That's exactly right. So this is definitely SN1. E1 was out. E1 is out because no beta hydrogen. So I backtrack for all primary. This is a guarantee. For all primary allylic or benzylic alpha sites, never ever can they go E1 or E2. So my decision is made on my nucleophile alone. If it's a weak nucleophile, it's definitely going to go SN1. And if it's a charged nucleophile, it's definitely going to undergo SN2. Again, if it's a weak nucleophile, it's going to undergo SN1. And if it's a charged nucleophile of any variety, moderate or strong, any charged, is going to undergo SN2. So my mechanism will proceed through that carbocation intermediate that I just erased, now not having all the hydrogens on it because we don't need it, right? Water's going to come in and attack at this site. So now I have this out of it. And then there is deprotonation in order to lend itself to the product that I'm going to get. Okay? Which is this product here. Does everyone see that? Are there questions about that? Okay, yeah.
So in this specific case, charged nucleophile is always SN2?
Charged nucleophile is always SN2.
But not always, not when it's like not benzylic.
Yeah, but when it's primary allylic or benzylic. So for this case, that's what I thought you meant, right? Primary allylic and benzylic. A charged nucleophile will always do SN2. Okay? All right. I'm going to put up 2 or 3 problems. I want you to try and work on them in the next few minutes because this is the chapter 17, stability issues. Then I want to say one other thing about SN1, SN2, and then we're going to go talk about the alcohol oxide ether reactions to remind you about those. So, you practice some examples, see where you go. I'm gonna give you 2 or 3 minutes to work on these, so you can see where you go with it on your own. That way, hopefully we can correct some of your thinking if you need to.
Building to the right, micro. You know your like stamp student union, and then there's that what? Yeah, Hormick. Yeah.
Okay, so you like, go across the street to Snap and then just make a right. I'm actually going down that way from my car.
I don't know what anything is. It's not sad thing. I know how to get here though.
Yeah, I had that same problem. I've been only going here for like 3 semesters.
Yeah, I never go.
You're really far down there.
Yeah, I know.
There's no hope for any of us.
I totally agree. I am very far. Totally agree. Okay.
All right, let's see where you went. CH3OH and heat. What type of mechanism?
SN1.
SN2?
SN1.
Okay, I'm at secondary allylic, right? Secondary allylic. Secondary allylic is like tertiary. Okay, great. I have a weak nucleophile. Did everyone remember to make the conjugate acid? This is conjugate acid CH3OH2+. Its pKa is minus 2.4 of the conjugate acid. Conjugate acid. Therefore, it's a weak nucleophile. Heat, secondary allylic like tertiary. What's this mechanism?
SN1.
E1, right? E1. It would be SN1 if the heat wasn't there. This is E1. E1. Okay? So the product is going to be creating the carbocation. The carbocation will not shift. Okay? Will not shift because secondary allylic is more stable than tertiary. I'm just making a statement out loud. Doesn't really change the product at this point, but I just want to let you know. This is the alkene that you're going to get, the new alkene that you're going to get from this reaction. Okay? So what makes this E1? It's a weak nucleophile at a secondary, well, like a tertiary site with heat. Heat is your indication that elimination is the favored product. Now, the last example we did was a trick, right? But it's not a trick because I told you the trick. Just so we can be clear, okay. So this is the product of this reaction. Okay, great. Next one. E2, SN2, E1, E, whatever the last one is. You know what I mean? This one's going to be, we got an SN2, we got an SN1. I'm not hearing the right mechanism yet. E2. everyone's seen it under handouts because the decision tree really helps us. So let's remind ourselves, it's tertiary benzylic. That's just like tertiary because I can't really do better than that, right? Tertiary benzylic. And I'm adding a charged nucleophile whose pKa's, conjugate acid HCN, pKa is 9, so it's a moderate charged nucleophile. Any charged nucleophile at a tertiary site is going to undergo E2. Okay? Any charged nucleophile at a tertiary site is going to do E2. The only things that are going to do SN1 and E1 are weak nucleophiles. That's it at tertiary sites. E2 is a really good competitor. I remind you, it's awesome. Remember to pull always from the more substituted carbon, okay? Beta site, more substituted carbon beta site, okay? So this is my product from this reaction. All right, last chance, redeeming, okay? I have a site that's secondary allylic, right? Secondary allylic. So that's just like a tertiary site, okay? This one might be tricky, actually. This one's probably going to be tricky. Yep, it is tricky. I can tell you already. So sodium is going to be canned in favor of SH minus. H2S is the conjugate acid. pKa is 7-ish. So it's a moderate nucleophile. What are we going to get?
SN2. SN2.
SN2. SN2. This one's definitely hard. Definitely hard. Okay? We are going to make a decision tree right now. Let's make a decision tree. We're going to make a decision tree that houses our allylics and benzylics. Okay? So this decision tree I'm going to type up after class. I'm going to talk you through it right now, but I am going to type it up after class and put it under handouts. Okay? So if you want to just listen to me talk through it, that's totally fine. Yeah?
So there was no beta hydrogen for the first one, and it would be SN1.
That's exactly right. Yeah. Okay. So here is our decision tree for the benzylics and allylics. So I guess our first decision is going to be, right, the first thing we're going to do to decide between which decision tree, right, because this is going to be the first thing I do. I think I'm going to blend the two decision trees together. Is the first thing I'm going to say is my alpha site benzylic or allylic. That has to be the first decision, right? If the answer is no, we're going to go to the decision tree that you already have, right? So this decision tree is going to be the one that's already online. If you printed that and you've been looking at that, that's where you're going to go. I'm going to make it so it's part of the handout, okay? But if the answer is yes, this is where we're running into a little bit of trouble. So this is where we're going to go and make a better decision tree, and this is what I'm going to be adding. So the answer is yes. My site is benzylic or allylic, okay? The question still is going to have to become, is it primary, secondary, or tertiary? Because we're still making a decision, primary decision, based on that classification. So I'm still going to say, is it primary, secondary, or tertiary? I can't go under here because it will get too small, so I've just wrapped around. Primary, secondary, or tertiary. So here, if I'm primary, I know I only have two mechanisms at hand, SN2 or SN1. That's it, right? First example showed us that. Primary allylic or benzylic can only do SN2 or SN1. So the question is my nucleophile charged? Which in essence you read out moderate or strong. Okay? If the answer is yes, this is going to be SN2. If the answer is no, this is going to be SN1. Those are your only two mechanism choices at a primary allylic or benzylic site because there's no beta hydrogen to pull. Okay? At a secondary site, really I have the ability to have all mechanisms. But this is like a true secondary site, okay, in some ways. So the question that I ask here, right, is what is the pKa of the conjugate acid of the nucleophile? And this is where I'm going to be separating, okay? So I'm going to say if it classifies as weak, I'm going to be SN1E1. You know the further discrimination there is heat. I will add that on, but you know if heat is present, E1 is major, SN1 is minor. And if heat is not present, SN1 is major and E1 is minor. Okay? If you classify this as moderate, you're at SN2, And if you classify this as strong, you're at E2. Okay? And then finally, we wrap around to if I have a tertiary site, SN2 is not possible at a tertiary site, so I really only have 3 mechanisms at play here. So I ask the same question. Is my nucleophile charged? And by that I mean, is it moderate or strong? Okay? Because if the answer is yes, this is going to be E2. And if the answer is no, this is going to be SN1, E1, with the play out being heat. If heat is present, E1 is my major product. If heat is not present, SN1 is my major product. Okay? So I will expand your decision tree handout over the next day and redeposit it online. Okay? And I will, with that, deposit some practice problems so you can try them. Are we at 11:50, 12:50?
Yeah.
All right, see ya. You come up, I'll answer your question.